Welcome to The Explainer. Today, we're taking abstract mathematical notation and transforming it into a highly visual, totally examination-ready masterclass on sets and functions. If you've ever felt completely intimidated by mathematical jargon, well, you're in the right place. We're going to break down everything from basic collections to complex mappings. And honestly, this isn't just for passing your DPE or competitive exams, though it will definitely help with that. These exact logical tools are the foundational building blocks that power modern computer science and artificial intelligence. So let's turn these concepts into clear, logical tools you can actually use.
Okay, so here is our roadmap for today. We've got a structured 5-step journey taking you from the absolute most basic definitions of sets all the way to mapping out complex mathematical functions. We've got quite a bit of ground to cover, but if you follow along step by step, you'll see exactly how all these pieces interlock perfectly.
All right, let's dive into Section 1, Introduction to Sets. We have to start with the foundation. What exactly do we mean when we talk about a set in mathematics?
So, the absolutely crucial point here is that a set is simply a well-defined grouping of things. It could be anything. Think of the set of former United States presidents, or maybe the set of vowels in the English alphabet. If we call our vowel set B, then the letter I is a member or an element of that set. And notice that little curved E symbol? That's our official shorthand in mathematical notation for stating that something belongs to a set. Now, to make this super concrete for your exams, there are some standard symbols you absolutely must memorize. You're going to see these everywhere. N stands for natural counting numbers, starting at 1, 2, 3, and so on. Z covers all of your integers, so that includes your negatives, your positives, and 0. P is for prime numbers, and Q captures rational numbers, which is basically any number you can express as a fraction. Seriously, knowing these letters on sight is going to save you so much precious time on test day. Moving right along to Section 2, Set Operations and Vens. Now that we know what sets actually are, let's see how they build into real mathematical operations. Okay, the most critical distinction you need to grasp right now is the difference between these two operations. A union, which is represented by that upward U shape, combines literally everything. Think of it like a massive party where if you're in set A or set B or even both, you are invited. But an intersection, that's represented by the upside-down U, and it is highly exclusive. It represents only the overlapping elements that are strictly in both A and B. It's kind of like the VIP room of sets. To really picture this, we use Venn diagrams. These were created by British mathematician John Venn back in the late 19th century. By putting overlapping circles inside a universal rectangular boundary, we can visually map out relationships. It's brilliant, really. You can clearly see how completely disjoint sets remain separate, while overlapping sets share that highlighted center region, which, by the way, is our intersection. Fun little historical fact, Venn actually called these Eulerian circles at first, but eventually his own name stuck. Let's anchor this concept with a real-world exam problem to test our logic. Imagine a high school with exactly 100 seniors. We need to figure out who plays where without accidentally double counting the busy students who are doing both band and orchestra. Now, the real trick to solving this puzzle is that center intersection. The 32 in the very middle represents the students doing both. By isolating them first, the 37 on the left are the ones only in orchestra, and the 18 on the right are only in band. When you add up those unique groups, plus the 13 kids sitting outside the circles who aren't in either music program, you get exactly 100. If we hadn't used that center intersection, we would have literally counted those 32 students twice. Okay, Section 3, Logical Proofs of Operations. With the visual operations making sense, it's time to rigorously prove these identities using step-by-step logic. By tracking just a single element, let's call it X, through the definition of a union, we can formally prove that the order of sets just doesn't matter. If X is in A union B, it inherently means X is in A, or it's in B. And because of basic English logic, saying A or B is the exact same thing as saying B or A. Therefore, X is in B union A. This kind of step-by-step logical deduction, it's the absolute heartbeat of mathematical proofs. But hey, we've got more than one tool in our mathematical toolbox. Instead of staring at walls of algebra, you can also prove complex laws visually. Take De Morgan's laws, for example. By using horizontal shading for one side of the equation and vertical shading for the other, you can physically see where the regions match up. When the grid pattern perfectly aligns across two different diagrams, boom, you've just visually verified a complex identity. Let's move to Section 4, Ordered Pairs and Products. We're ready to combine sets in a totally new way. I want you to think of a Cartesian product as strict mathematical matchmaking. Unlike our previous operations where the order inside those curly brackets didn't matter at all, here, the specific order of your x and y coordinates is absolutely essential. Every single element from set A gets paired with every element from set B, creating highly specific directional coordinates. Putting elements out of order here is literally like trying to put on your shoes before your socks. It just doesn't work. Let's look at the actual numbers. This simple multiplication principle tells us that a set of 3 elements times a set of 2 elements is always going to yield exactly 6 unique ordered pairs. You just map them out logically, right? 1 pairs with 2, then 1 pairs with 5. Then 2 pairs with 2 and 5. Then 3 pairs with 2 and 5. It is incredibly organized, highly predictable, and it's the foundation for what comes next. And that brings us to our final stop, Section 5, Understanding Mathematical Functions. Let's take those ordered pairs and apply a rule to them. The crucial takeaway here is that a function acts as a processing machine. It takes an input from your starting set, which is what we call the domain, runs it through a specific mathematical rule, and then strictly maps it to a single output in your destination set, which we call the range. That's exactly why you always see it written as y equals f of x. The x goes in, the f rule happens, and the y pops out. You can literally trace these rules in action. Just follow the arrows from the inputs in the first set to their assigned images in the second set. Sometimes every single input gets its own completely unique output. Other times, multiple inputs might point to the exact same output. And sometimes, there are leftover numbers in the second set that never get mapped to at all. These visual paths dictate exactly what kind of function we're dealing with. I highly, highly recommend you memorize this table for your exams. Knowing the difference between these types is a guaranteed way to secure easy marks. Let's run through it. First, if there is an element left lonely and unmapped in set B, it's an into. Second, if every single element in set B is hit by an arrow, it's onto. Third, if every input gets its own totally unique output with zero sharing, it's one-to-one. And finally, the absolute gold standard, the bijective function. This perfectly achieves both one-to-one mapping and onto coverage. Nothing is left out and nothing is shared. So as you wrap up your studying, I really want you to consider this. These aren't just dry, abstract rules for a math test. Mastering these basic logical groupings and rules of input and output might actually be the ultimate key to unlocking advanced mathematics, data science, and even the complex neural networks that are powering artificial intelligence today. It all starts right here, with sets and functions. Keep studying, keep mapping out your logic, and I'll see you in the next explainer.